Well, sort of an interesting statement right here that compound interest is the eighth wonder of the world. He who understands it earns it. He who doesn't pays it. And that was from Albert Einstein himself, the one of the great thinkers in history here. So maybe we actually have a real cool thing here. Hopefully, we realize that. So let's talk about how does compounding interest work in this formula. Well, let's find the balance of an investment of $6,500. And let's say we have an annual interest rate of 3.5%, and we're going to compound it monthly for 5 years. All right, so T is the time in years, right? If we think about how this model works, as we explained in the last video, T is the time in years, and we want to invest for 5 years in our example right here, right? So we're going to set that to 5. Our annual interest rate, well, it's 3.5%, but whenever you enter in your annual interest rate, we always give the decimal form of that, so we're going to write it as 0.035 to operate with this model. Principal, well, the principal is the amount of money that we actually put into our account to start it off, and so we're going to start with a principal of $6,500. This is what we're interested in, our account balance. We don't know that yet, but we said it's a number of compoundings per year. And if we say the word monthly, that implies that our number of compoundings will equal 12. So let's work out what we're going to get for our account balance. Based on this formula, we can say that if we take a principal of $6,500, we're going to multiply it by 1 plus the rate, which we write as 0.035, divided by n, in this case that's 12, but we're going to take that 12 times 5 and work out the values that we get right here. Okay, now just for the sake of illustrating with an in-between step, I'll show you what this actually looks like sort of as an in-between step. I'd be taking 6,500 and multiplying it by 1 point something. And what is that going to be? Well, let's work this out. We said it was 0.035. That's 3.5% divided 12 ways, and we add 1 to that. So we're going to say 1.0029166666667 and so on. We'll go ahead and just carry this out here a little bit. You actually want to carry a lot of digits right here. If I were writing this out on my paper, I would write right now 0, 0, how many zeros there? 2 zeros. I have to keep looking back. 2, 9, I believe it was 1, 6, 7, right? Those 1 6s were continuing, so I'll write a 7 if I'm rounding it up. Raised to the 12 times 5, 60th power. All right. Well, I'll cut to the chase right here. What's going to happen if we actually work this out? Well, all right. We're going to raise this to the 60th power. So that's that result raised to the power 60. So I'm going to take 1.19094, and you want to carry as many digits as you can as you're doing this calculation. Trust me, because if you round off right here with this base, you're going to be into a lot of trouble. If you round, you can lose dollars and cents. And if you're a banker or something else dealing with some sort of interest, believe me, the more dollars and cents off you are, the worse it gets for you, right? So you're going to take this and you're going to multiply it by 6,500. And let's get our result. We get 7,741. And 1, 2, we've got an 8 after the 2. Since it's higher than 5, we round up. So we'll say our account balance at the end of that 5 years would be $7,741, and just making sure my digits right here, 13 cents when rounded up. All right, so this would be my account balance after 5 years. Now you can imagine what's going to happen. Obviously, if I increase the number of years, that amount increases. If I increase the number of compoundings, this amount would also increase, by the way, too. So it's sort of an interesting thing. All right, so let's try one more model. This time, what happens if we continue increasing the amount of compoundings.